So now we're to part 3 in chapter 4. In the first two parts, we have learned some new types of chemical reactions. We've learned about solubility rules, electrolytes, molecular ionic and net ionic equations. So the last video, we ended with molecular ionic and net ionic equations, and we practiced doing those on metathesis reactions. But just so you know, every type of chemical reaction, any of the categories we talk about, can be broken down from molecular to ionic to net ionic, assuming that there is at least one chemical that is a strong electrolyte. If none of the chemicals are strong electrolytes, then the molecular equation is the same as the net ionic equation. But so just because we practiced it for metathesis reactions, we can do net ionic equations for all of these types as well. So what we're going to do is we're just going to kind of pick up on the types of reactions. We're going to learn some new types of reactions. We've got a little bit of background that we have to talk about to get into this though. So we're going to go back over acids. So acids are something that we talked about in chapter 2 when we were naming them, and we recognized an acid was a substance that began with an H. Okay, so and in this chapter, our acids all start with hydrogen, and they're going to be all aqueous for us. Now, we have differentiated them into the 7 strong acids and then weak acids. The 7 strong acids dissociate 100%, and the weak acids dissociate some, but not all the way to 100%. So looking closer at acids, we're going to have some definitions of what actually makes an acid. And there are actually 3 different definitions. We're only going to look at 2 of them this semester. And this is one of those times where you need to know the scientist's last name and then what their contribution was. So the first scientist's name we're going to focus on is Arrhenius. Okay, so Arrhenius is the scientist, and he had a definition of what acids were. And his definition is that acids increase the amount of H pluses when they're dissolved in water. Okay, that's his definition of an acid. So with the Arrhenius acid, it has to be dissolved in water, so it has to be aqueous, and it has to contain an H so that way it can dissociate, and one of those things that it dissociates into are H pluses, so it's increasing the amount of H pluses when it dissolves. The second set of scientists that we need to know for their definition is Bronsted-Lowry. Okay, so Bronsted and Lowry are 2 different scientists, but they came up with the same definition in the same year after there being evidence that they've never talked to each other. So they have to both share the title of this definition. So the Bronsted-Lowry definition of an acid is a proton donor. Now you might look at that and be like, okay, that's what? So H pluses are the thing that the Arrhenius definition was focusing on. So let's think back to chapter 2. H plus. I want us to figure out the number of protons and electrons in an H plus ion. So H is hydrogen. We look on the periodic table. The number of protons is the atomic number, so it has 1 proton. It's got a positive 1 charge, so if it was neutral, it would have 1 proton and 1 electron. It's got a positive 1 charge, which means it has 1 more proton than it does electrons. So doesn't that mean if it has 1 proton, it had to have 0 electrons? So for the Bronsted-Lowry definition, a proton is the same as an H plus. So a proton donor means it gives away H pluses, which is similar to the Arrhenius definition. But one major difference is the Arrhenius definition clearly spells out that the acid has to be dissolved in water. Notice that the Bronsted-Lowry definition just says, oh, they have to donate H pluses. It could be in air, it could be in oil, it could be in cyclohexane. It doesn't matter what it's dissolved in. Okay, so the Arrhenius definition is more specific. Fewer things meet the Arrhenius definition, more things meet the Bronsted-Lowry definition. So this is a reminder, there are 7 strong acids, which are strong electrolytes that dissociate 100% of the time. They are HCl, HBr, HI, HNO3, H2SO4, HClO3, and HClO4. So all of them, their names here, what I didn't add was the last word of all of their names is acid. It's hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, chloric acid, and perchloric acid are the 7 strong acids. Okay, I do not have a list of all of the weak acids. All of the weak acids are anything that starts with hydrogen that are not these 7. So that's why it's important for us to know the 7 strong acids, so you can recognize the weak acids by process of elimination. Okay, so let's look at bases. Same 2 scientists, but we have a new set of definitions for bases. According to Arrhenius, his definition of a base is something that increases the concentration of OH minuses, so hydroxides, when it's dissolved in water. So this definition is very similar to the Arrhenius definition for acids. It's just acids were H pluses. and bases were OH minuses. Okay, so that's the Arrhenius definition. So 2 sets of definitions. So we're going to have the Bronsted-Lowry definition. The Bronsted-Lowry definition is defined as a proton acceptor. So just a quick reminder, as far as we're concerned, protons are H pluses. So a proton acceptor, an H plus acceptor, well, that's not at all close to the Arrhenius definition of a base. The Arrhenius definition of a base, it increases the OH minuses when it's dissolved in water. The Bronsted-Lowry doesn't mention water or OH minuses. So again, the Arrhenius definition is super specific. It's very narrow viewed. The things that meet this definition, the Arrhenius definition of a base, they are bases, but it just turns out more things are bases than the things that meet this definition. Arrhenius was too narrow in his definition. He missed some stuff. Okay, so the Bronsted-Lowry definition is more broad, more general. Okay, it doesn't mention water and it doesn't even mention hydroxide. We're going to look at some examples of the Bronsted-Lowry definition here pretty quick. But another reminder, the 8 strong bases are listed here. We need to recognize those. Just because it contains a hydroxide does not make it a strong base. Only these 8 are strong bases. So remember the solubility rules earlier in the chapter? Hydroxide is one of the rows of the solubility rules. Hydroxide is in the insoluble section. And then there's a list of exceptions. It turns out these are all of the exceptions. So really, you don't necessarily have to memorize the strong bases if you just remember the strong bases are the soluble hydroxides. And then everything's good. Okay. So earlier in the chapter and on one of the on the handouts that are in the Canvas page, this is listed. The 7 strong acids and the 8 strong bases are all here. So this has already been said. Okay. But I just wanted to show you how it all is in one place. So these compounds are all strong electrolytes. So what we're going to do now is we're going to go to our next category of reactions. So far we've learned about combination, decomposition, combustion reactions from chapter 3. We added precipitation reactions and metathesis reactions in our last lecture video in chapter 4. So now we're going to add some more. So our next category is acid-base reactions. Now, this is going to be so shocking. An acid-base reaction is when an acid reacts with a base. I love the names of some of these. It's so straightforward. So what we're looking for an acid-base reaction is if one of the reactants is an acid and the other one is a base. Now that could be following the Arrhenius definition or the Bronsted-Lowry definition. So the picture that I'm going to show here is going to be following the Bronsted-Lowry definition. So I'm going to rewrite, or actually it's going to show up down here. Here's the equation just written the way we normally look at them. Okay. Now looking at this, you might not automatically be like, oh, well, it's obviously an acid-base reaction. Neither of our chemicals that we're starting with are any of this, the 7 strong acids or the 8 strong bases. Notice that it doesn't call it the strong acid and strong base reaction. It just says acid-base reaction. So for the Bronsted-Lowry definition, let's just review really quick. For acids, they are proton donors. So I'm going to say H plus donor. And bases are acceptors, H plus acceptor. Oh, my pen. Okay, so when I'm looking for the Bronsted-Lowry definition, what I do is I count the hydrogens to see, did they donate them, which would mean giving it away, or did they accept them, which would mean to gain them. So I'm going to look at each thing in this balanced chemical equation and count the hydrogens. So in H2O, there are 2 hydrogens. In NH3, there are 3 hydrogens. In NH4, there are 4 hydrogens. And in OH minus, there are 1 hydrogen. Okay, so what I want to do to figure out if I have a Bronsted-Lowry acid and a Bronsted-Lowry base is let's look at the hydrogens before and after. So H2O, so I'm looking at oxygen. Oxygen starts with 2 hydrogens and ends with 1 hydrogen. Well, it obviously did something with its hydrogens because the number of hydrogens changed. Well, if it started with 2 and it ended up with 1, which definition do you think this meets? Either donating or accepting the hydrogen. When you donate something, like you give something to Goodwill or you donate food to a food pantry or whatever, you donate your time when you volunteer, aren't you giving it up? So if you start with 2 and end with 1, you gave up 1. So that means oxygen in this situation, or H2O as a whole molecule, is a Bronsted-Lowry acid because it donated a hydrogen. If oxygen started with 2 hydrogens and ended with 2 hydrogens, it would not meet this definition at all because it wouldn't be an acid or base. Okay. Well, let's look at the other scenario. So nitrogen starts with 3 hydrogens and ends with 4. starts with 3 and ends with 4. So didn't it gain 1? So it accepted a hydrogen. So that would make this a base. So this is an example of an acid-base reaction because one of the reactants is an acid and the other one is a base. Whatever we make isn't actually important. It's important that you start with an acid and you start with a base. For the most part, these acid-base reactions in general, most of them, the ones that you would be expected to predict, follow the metathesis. So they behave most of them, the ones that you're going to be expected to predict the products of. This is one that I would not expect you to predict the products of. This is one that I would have to give you the equation. Okay. So an acid-base reaction, you take an acid and you react it with a base and you make something. Okay. Acids are the ones that are easier to identify most of the time. Most of the time, acids start with an H, right? But now that we have this Bronsted-Lowry definition, that may or may not be true. It's all about counting the hydrogens. Okay, so that's a new one to our list. Acid-base reaction was added right after metathesis. I'm going to move on to neutralization reactions, which are actually a subcategory of acid-base reactions. If it's a neutralization reaction, it automatically meets the criteria of an acid-base reaction. It just has some more specifics here. So if you look at the scenario, well, the definition of a neutralization reaction is you take an acid and you react it with a base. That's why it meets the acid-base reaction. But for it to be neutralization, more specifically, one of your products has to be water, and then your other one is just whatever is left. So it's going to still follow that. It's going to follow the metathesis. Sorry, I was difficult to write and think and talk were all just, that's too many things. There's 3 things happening at once. So if it's an acid and it's going to meet the neutralization reaction, it's going to start with an H. If it's a base and it's going to meet the neutralization reaction requirement, it's going to end with an OH. So when H and OH come together, that makes H2O. And then those 2 things are going to come together to make the salt. So it follows the metathesis reaction procedure. It's just, it looks like this. So here's an example of an actual reaction that meets that definition. Acid, base, something, and water. So the salt is like something, like whatever's left. It's the thing. And we would still have to use solubility rules to figure out that this is aqueous. Okay, so this meets the definition of acid-base reaction and of neutralization. The added thing for neutralization is one of the products has to be water. It's an acid plus a base, arrow water and whatever. Okay. So here's another example of a neutralization reaction, which also meets the acid-base reaction scenario. Let's go ahead and do the ionic and the net ionic equation. So that'll be good. Okay, so we're going to have to think back to what we did. So with in the last video, step number 1 was to have the balanced molecular equation. Check. Step number 2 was to identify strong electrolytes. So strong electrolytes are the 7 strong acids, the 8 strong bases, and soluble ionic compounds, where we look at the solubility rules to figure that out. So first it's to look for acids. Are there any acids? Yep, HCl is an acid. Okay, starts with an H. Is HCl one of the 7 strong acids? So then we'd refer back to our handout. And yes, it is. So it's a strong acid, so I'm going to write strong electrolyte. NaOH, when you look at that, you may recognize it's a base. And even if you don't, you're like, oh, well, it's an ionic compound. Let's look at the hydroxides in the solubility rules. Well, the hydroxides in the solubility rules are in the insoluble section, but sodium is one of the exceptions. So this is soluble, so it's a strong electrolyte. Sodium chloride, it's an ionic compound, so let's look at the solubility rules. Cl minus, it's in the soluble section. Sodium is not one of the exceptions, so this is a strong electrolyte. And then H2O, well, if something's a solid, a liquid, or a gas, it's going to be a non-electrolyte. So when I go to do my ionic equation, I'm going to have to break apart HCl, NaOH, and NaCl. I'm going to leave H2O together the way it is. So that's where this came from. HCl became H plus aqueous and Cl minus aqueous. NaOH became Na plus aqueous and OH minus aqueous, arrow. NaCl became Na plus aqueous and Cl minus aqueous, and H2O stayed the same. Now, let's look at spectator ions. Well, because it's going to be cancel out spectator ions to go onto the net ionic equation. Well, H plus is not a spectator ion. I don't see it on the other side. Cl minus is a spectator ion because I see it exactly the same before and after. And A plus is, I can cancel that out. OH minus is not. So I have two spectator ions, chloride and sodium. So what's left, I'm just going to rewrite it. H plus aqueous and OH minus aqueous equals H2O. This is a pretty common net ionic equation when we're dealing with neutralization reactions. If you're starting with a strong acid and a strong base, this is what it's going to look like. So I also wanted to point that out because there are times where you might do multiple questions and you get this is the answer to multiple problems. You might think, well, I must have done it wrong because I got the same answer. No, this is a pretty common net ionic equation, so don't be freaked out if you get it multiple times. So what I want us to do is to practice either these acid-base reactions or neutralization reactions. And I want us to do this, apply the ionic and the net ionic to this. Okay, so I'm going to start with this question. It says to write a balanced molecular equation for the reaction of aqueous carbonic acid and potassium hydroxide. So we got to think back to chapter 2. Oh my gosh, I gave you names and you have to come up with formulas. I'm the worst. All right, so carbonic acid. Well, when we're dealing with naming rules, if it's an acid, it starts with a hydrogen. So I know it's going to say H. Based on the naming rule, it does not have hydro in front of it. It just ends in ic acid, which means the polyatomic is an 8. So this is going to be carbonate, which is CO3 2 minus. So when I put this together to make the charges cancel, it's going to be H2 CO3, and it says aqueous. And then the next name says potassium hydroxide. So potassium, we have to remember, is K. Look on the periodic table, it's in group 1. K plus. Hydroxide is a polyatomic ion, OH minus. So when I make this for the charges to cancel, it's KOH. It's soluble according to the solubility rules. So H2 CO3 aqueous plus KOH aqueous. What we're going to do is predict products by following the the net ionic, oh my gosh, words, metathesis scenario. So we need to come up with the 4 ions and flip-flop them. So this is made up of the hydrogen ion and the carbonated ion, the potassium ion, and the hydroxide ion. So on the other side, I'm going to have hydrogen paired with hydroxide, and I'm going to have potassium paired with carbonate. So the order in which I write these doesn't matter. Let's do the H and the H plus and the OH minus. So if you want to, you can write this HOH. But what I want you to recognize is that is the same thing as H2O. And H2O, unless I tell you otherwise specifically, is going to be a liquid. Okay. My other compound is going to be potassium ion and carbonate ion. When I make a compound with that, it's going to be K2CO3. I would have to check the solubility rules. Carbonates are in the insoluble section, but there are a set of exceptions, and potassium is one of them, so this is going to be aqueous. Now when I go to balance this, I'm going to need to do this and this. 2 hydrogens, 1 carbonate, 2 potassiums, 2 hydroxides. Okay, so that would be my balanced molecular equation. I'm going to clean this up a little bit. I'm going to actually erase this and write H2O. There, and I'm going to erase my work that got me to this point. Because next I want us to write the ionic and the net ionic equation. So what we need to do is decide which ones are strong electrolytes. So strong electrolytes, the 7 strong acids, the 8 strong bases, and the soluble ionic compounds. So first, let's look for acids. Do you see any acids? Well, H2CO3 is an acid. Okay, one hint is that it says acid right there. Another one is that it starts with hydrogen. So H2CO3, it's an acid. Is it one of the 7 strong acids? So we need to refer back to our chart. And no, it is not one of the 7 strong acids. So this would be a weak electrolyte. Potassium hydroxide, you can either look at that and recognize it's one of the 8 strong bases, or it's an ionic compound that if we look at the solubility rules, it is a soluble ionic compound, so it's a strong electrolyte. H2O liquid, if you looked at that and you thought it was an acid, because it starts with hydrogen, it's not one of the 7 strong acids, so it would be a weak electrolyte. Reality, it's a liquid, so it's a non-electrolyte. And then K2CO3 is an ionic compound. It's not an acid, it's not a base, it's an ionic compound. According to the solubility rules, it's soluble, so it's a strong electrolyte. So when I do this, only the strong electrolytes get dissociated. So this and this, I am going to break apart. Okay. The other two things are going to stay together. I don't know if that looks gross. Okay, so H2CO3 stays together. 2 KOHs became 2 K plus aqueous and 2 OH minus aqueuses. K2CO3 became 2 K plus aqueous and carbonate aqueous, and the two waters stayed two waters. So that's the ionic equation. If I want to go on to the net ionic equation, do you see any spectators? I see one. Potassium ions. So those cancel. And what I have left is this. My net ionic equation really didn't get that much smaller. Okay. Sometimes net ionic equations are big. Okay. What I want is for you to practice this next one. So I went all the way like full evil mode where I gave you the name and you have to come up with the formula for the two reactants, and then I want you to predict the products. Use your solubility rules to figure out the ions, balance it, and then I want, well, let's start there. Okay, so start there. Let's come up with, so hit pause. I want you to write the balanced molecular equation for this. When you're done, go ahead and hit play and we'll go through it together. So let's go through it now. So aqueous phosphoric acid. So I've got to turn that name into a formula. Well, it's an acid, so it's going to have H pluses in it. Phosphoric acid, well, ends in ic. So it's going to be phosphate, which is PO4 3 minus. So that is going to be H3 PO4 to make the charges cancel. And barium hydroxide. Well, barium is Ba. We look on the periodic table, it's a 2 plus. Hydroxide is an OH minus polyatomic. So to put those together so the charges cancel, that's what we have. Okay, those are my two reactants. Both of them are aqueous. We go to predict our products. Positive charge here is going to go with the negative charge there. Positive charge here is going to go with the negative charge there. Then I'm going to have to look at solubility rules. So when I put this all together, barium hydroxide and phosphoric acid becomes barium phosphate, which is insoluble, and water, which is HOH, which is a liquid. And then to balance it, it wasn't super straightforward. We had to do a little bit of work to get it balanced. Hopefully that went okay. Okay, so if we got here, what I want you to do now is start from right here, determine which of these are strong electrolytes, and dissociate those strong electrolytes to write the ionic equation. And then look for spectator ions, cancel out any spectator ions you find, and come up with the net ionic equation. And then when you're done, hit play again, and you can check, and we'll go through this together. Okay, so let's look for strong electrolytes. So strong electrolytes. 7 strong acids. Well, do we see any acids? Yep, H3PO4. Is that one of the 7 strong acids on that chart? No, it's not. So it's a weak electrolyte. It's not a strong electrolyte because strong acids are strong electrolytes. Weak acids are weak electrolytes. Okay, and this, I'm going to go ahead. This is a non-electrolyte because it's a solid. And this is a liquid, so it's a non-electrolyte. But barium hydroxide is aqueous, so we got to decide. First, it's not one of the 7 strong acids. We could recognize it is one of the 8 strong bases, which makes it a strong electrolyte. If you didn't recognize it was a base and you just saw it as an ionic compound, you could look at the solubility rules for hydroxide and it is soluble. So of these 4 compounds, the only one I'm going to break apart is barium hydroxide. H3PO4 stays together because it is not a strong electrolyte. Ba3PO42 is not a strong electrolyte, so it stays together, and H2O is not a strong electrolyte, so it stays together. So when I break apart barium hydroxide, leaving the other 3 the same, this is what I see. 3 bariums and 6 hydroxides, and the 6 hydroxides came from the 3 times the 2 right there. So then now it's time for us to look for a spectator ion. Do you see any spectator ions? No, this is both the ionic equation and the net ionic equation, and there were no spectator ions. Yeah, that's a thing. Okay, so don't be surprised if that happens. It doesn't happen all the time, but it definitely happens. Okay, so we've now learned acid-base and neutralization reactions. Okay. Our last category of reactions for this video is gas-forming reactions. Any guesses on what happens in a gas-forming reaction? If you guessed it forms a gas, then gold star. So in gas-forming reactions, one of our products is a gas. Okay, now gases, we don't have a set of solubility rules for the gases. That's not a thing. So you're not expected to memorize which things are gases. You'll be given information to help you figure out which things are gases. But for right now, let's just look at balanced chemical equations and see if we can recognize if they are a gas-forming reaction or not. So for this one, isn't this a gas? That makes it a gas-forming reaction. Yay! What you would see in the lab is this would make bubbles. Okay. What happens is H2CO3 is actually the product that you would expect to see when hydrogen and carbonate come together. In real life, once carbonic acid is formed, it often decomposes into carbon dioxide and water. Carbon dioxide is a gas. So that's just showing what actually happened. Okay. So that's how that occurred. So this reaction, this is also gas forming because I made a gas. Like that's really all we're looking for to see if something's gas forming or not. One of the products is a gas. So sulfurous acid also does the decomposition. So we made a sulfur dioxide gas. And so I just wanted to list the types of chemical reactions we have learned so far. So we have learned combination, decomposition, combustion. Those are from chapter 3, so I'm going to change colors. They still count, I just so that way you know where they came from. The first one we learned in chapter 4 was precipitation. Then we learned metathesis, which are also called double replacement, double displacement, exchange, all those things. Then we learned acid-base in this video, neutralization, also in this video, and then our last one was gas forming. We're not done. There are more, and oops, that's not how you spell gas forming. More to come, but that's a good place for us to stop at this point. So you're going to be very knowledgeable about the different categories of chemical reactions at the end of chapter 4.